Hello, and thank you for tuning in. My aim in this talk is to provide a big picture overview to the challenge of climate change. So let's begin by asking questions like, what is happening to the climate? And how may climate change impact Singapore and other parts of the world? So firstly, what has been happening to the climate? Well, the world has been warming over the last 100 years. These graphs show the change in annual mean surface temperature, starting in the year 1850. The top graph shows the annual averages, whereas the bottom graph shows the decadal averages. You'll notice, if you look at the top graph, that there are quite a lot of wiggles, and these wiggles show that there is interannual variability in the global mean surface temperature between different years. These wiggles are actually primarily driven by El Niño and La Niña cycles. If you don't know what El Niño is, that's okay. You can just think of it as a pattern of climate variability. Generally, where you get a peak, that often corresponds to an El Niño year. The important thing to note is that the warming trend is a lot larger than the interannual variability, showing that the world has indeed been warming. But what about the hiatus over the last few years? If you look at the top right, you'll notice that the warming trend isn't as steep as it was during the 70s and 80s. There are many possible reasons that have been suggested to explain this. Personally, I think it can be helpful just to think of it in terms of natural variability. You'll notice that there's other periods where there didn't seem to be much warming for 10 years, 15 years, 20 years. And I'd fully expect the rate of warming to actually increase again soon. And this year may actually end up being one of the warmest years on record now that we're entering an El Niño phase. But what is the reason for this warming? Over the same period, carbon dioxide concentrations in the atmosphere have also been increasing as a result of the burning of fossil fuels, such as coal, and also partly as a result of deforestation. Tropical deforestation of peatlands in Indonesia actually plays a major role. In tropical peatlands, carbon has accumulated over thousands of years, and when these peatlands are drained, that carbon can be released to the atmosphere, especially when it is accompanied by burning, by fires. So tropical deforestation in countries around Singapore not only contributes to the haze air quality problem we have, it not only contributes to biodiversity loss, it also contributes to climate change. But how do we know that the increasing concentrations of carbon dioxide and other greenhouse gases are responsible for the warming that we have seen over the last few decades? In fact, why should we expect increasing concentrations of carbon dioxide to warm the climate at all? Well, although skeptics may not realise this or acknowledge this, the science of the greenhouse effect is actually very well established. Well over 100 years ago, a researcher called Arrhenius pointed out that if the quantity of carbon dioxide increases, the temperature will increase. He even got the right scaling law, not bad for 1896. What Arrhenius had realised is that gases like carbon dioxide can absorb lots of the infrared heat radiation being given off from the ground, therefore trapping more heat in the climate system. We should actually be very thankful for this greenhouse effect. If it wasn't for the natural amount of carbon dioxide which naturally exists in the atmosphere, then the world would be a lot colder than it is now. It's even likely that in Singapore, in the tropics, we would be buried under a layer of ice. So the greenhouse effect is actually a very good thing. The problem is that we've been pushing the system out of balance by adding too much more carbon dioxide and other greenhouse gases. So, we would expect the world to warm as we emit carbon dioxide. But the world doesn't always work the way we expect it to. In reality, the climate system is very complex, with many different components such as the ocean, the atmosphere, land, sea ice, and many interactions between these different components. Nowadays, we have wonderful tools that help us to explore many of these complex interactions. These tools are the global climate models. These pieces of computer software represent three-dimensional atmospheric movements, a three-dimensional ocean, land processes, ice processes, and many of the interactions. You can basically think of the climate models as lots and lots of physics and chemistry written in 1 million lines of computer code. The models aren't perfect, but they are very useful tools to help us to understand the climate system as well as make projections of future climate. Let's look at what the models tell us about the climate change, in particular the warming, that we've seen over recent decades. This graph again shows us the global mean surface temperature during the 20th century. It shows the change in that global mean surface temperature. The black line represents observations, basically a smoothed version of the wiggles that we saw in the earlier graph. So we can see that there has been warming. The pink shaded region shows the results for several different model simulations that have taken into account both natural and human influences on the climate system. You can see that that pink shaded region matches the observations quite well. The blue shaded region shows the model results for simulations that have only taken natural influences on the climate system into account. And this blue line cannot capture the warming that we've seen. So what these model results suggest is that natural factors alone cannot explain the warming that we have seen during the 20th century. As well as helping us to understand past climate, these models are also useful tools helping us to understand possible future climates. They can provide projections of global and regional temperature and rainfall and so on. Let's start by looking at projections of the global mean surface temperature. So this graph is showing some projections of the global mean surface temperature up to the end of the 21st century. The red line and shaded region shows results for a business as usual scenario, assuming that we'll continue emitting a lot of greenhouse gases as we are doing currently. The blue line shows results for an aggressive mitigation scenario, which assumes that we will rapidly reduce our emissions of carbon dioxide and other greenhouse gases. There are two main sources of uncertainty in these future projections. The first source of uncertainty comes from the fact that we don't fully understand how the climate system works. Basically, the models aren't perfect. So we can refer to this as physics uncertainty or model uncertainty. This uncertainty range can be tested to some extent by using many different climate models. And this uncertainty is represented by the shading. So the shaded region shows the results for several different models and therefore gives an indication of this physics uncertainty, the model uncertainty. The second source of uncertainty is associated with the fact that we don't fully know how much more we will emit in future. In particular, we don't know about the future economy, whether we will be able to reduce our carbon dioxide emissions. So this is known as emissions uncertainty. And this can be represented as a difference between these two scenarios, the red business as usual scenario and the blue mitigation scenario. As you can see, the closer we get to 2100, the more the emissions uncertainty dominates. As the IPCC says, continued emissions of greenhouse gases will cause further warming and changes in all components of the climate system. Limiting climate change will require substantial and sustained reductions of greenhouse gas emissions. To paraphrase this, it's basically saying that how bad climate change gets depends on our choices now. Let's consider other possible future changes such as rainfall. With rainfall, the uncertainties are larger. The global climate models have a bit less skill when it comes to projecting future regional changes in rainfall. However, we do fully expect many parts of the world to get wetter and other parts of the world to get drier. And this could have an adverse impact on water resources, on ecosystems, on human livelihoods, and on agriculture. So changes in precipitation will probably be very important in many parts of the world. What about flooding in Singapore? May we expect to see more or less flooding in future? Well, using high-resolution regional models, Singapore's second National Climate Change Study, produced by the Centre for Climate Research Singapore, has concluded that most of these regional models show an increasing trend in the intensity and frequency of heavy rainfall events over Singapore and the surrounding region. So, flooding may become more common in Singapore in future. What about other extreme events? With many types of extremes, like tropical cyclones, hurricanes, the uncertainties are very large. It's still very uncertain how climate change will impact tropical cyclones, though a lot of people are now looking into this. When it comes to heat waves, we have a lot more confidence to say that over many parts of the world, heat waves will become more common as the world warms. By the way, when we talk about extreme events and attributing extreme events to climate change, we cannot say that climate change caused any one particular extreme event. Instead, we need to think in terms of probability. So, for example, we cannot say that climate change caused the 2003 heatwave in Europe that killed many people. But we may be able to say, as one study has done, that climate change made that heatwave more than twice as likely to occur. It's a bit like playing with weighted dice. If we roll 4 normal dice, we may end up with 4 sixes all at once. But if we roll some weighted dice, the probability of getting 4 sixes may increase by quite a lot. What about the Arctic sea ice? Did you know that in 2013 Singapore was given permanent observer status on the Arctic Council? In Singapore, we're a long way from the Arctic, so why is our government interested in the Arctic? Well, I suggest that one possibility may be to do with shipping routes. At the moment, a ship travelling between China and Europe needs to travel via Southeast Asia. This is one reason why Singapore is such a successful port city. However, as the Arctic sea ice melts, soon ships may be able to travel between China and Europe by going across the Arctic in summer, which is a much shorter distance. So this may mean that fewer ships come through this region in Southeast Asia, and this may have a negative impact on Singapore's economy. What about sea level rise? Sea levels are currently rising at a rate of around 3 millimetres per year. This may not sound much, but it does add up. At the same time, many cities in this region are sinking at a rate of up to 10 times faster than this. The problem is that too much water is being pumped up from the ground, and the ground is sinking as a result. For example, parts of Ho Chi Minh City are sinking at a rate of 8 centimetres per year, parts of Jakarta at a rate of 10 centimetres per year. This adds up to 1 metre in 1 decade. As these cities sink and as the sea levels rise, this may make flooding a lot more common. Focusing on just the sea level rise aspect, the IPCC estimates that under a business as usual scenario, sea levels could rise by up to 1 metre or so this century. The sea levels will continue rising, of course, in future centuries due to the fact that there is a delayed effect of the warming on the ocean. It's worth noting, however, that this upper bound of 1 metre this century assumes that there is no catastrophic melting of the Greenland or Antarctic ice sheets. If large-scale melting of Greenland or Antarctica was to occur, then this could mean that sea levels could rise by several metres very fast. And this would be devastating for many low-lying areas, especially small islands. And many cities, of course, that are in coastal areas. It's worthwhile noting that those who will be impacted most by climate change are the poor and the vulnerable. So climate change is very much a social justice issue. The second working group of the IPCC says that people who are socially, economically, culturally, politically, institutionally or otherwise marginalised are especially vulnerable to climate change. And throughout the 21st century, climate change impacts are projected to slow down economic growth, make poverty reduction more difficult, further erode food security, and prolong existing and create new poverty traps, the latter particularly in urban areas and emerging hotspots of hunger. So, for example, sea level rise may impact the lives of millions living in Bangladesh. Lots of Bangladesh is very low-lying, only a few centimetres or a few metres above sea level. There isn't a lot of free land due to the fact that Bangladesh has a very high population density and the people cannot afford to adapt. So as more land is lost to the sea and flooding, this may create millions of climate refugees. Climate change may increase the frequency of drought in many places, impacting agriculture, the livelihoods of poor farmers who may have no other source of income. And climate change may even contribute to armed conflict, such as the wars that are currently ravaging Syria and Iraq. There's actually evidence to suggest that climate change may have contributed to the drought that has affected Syria in the last few years, and that this drought has in turn contributed to the instability in the country that has contributed to the civil war. This is very controversial, but it's possible that climate change has facilitated the rise of IS. So, we need to do something about climate change, but reducing our emissions is very hard. What if there was an easy way out? Many people have suggested that we could deliberately engineer the climate system as a way to combat climate change. This is sometimes referred to as climate engineering or geoengineering. It's important to recognise that there are two main types of climate engineering. The first is known as carbon dioxide removal geoengineering. The idea is to remove carbon dioxide from the atmosphere that has already been added to the atmosphere by the burning of fossil fuels. So one of the popular proposals is called bioenergy with carbon capture and storage. The idea is that you can burn biomass from crops or trees to produce electricity, and then the carbon dioxide could be captured and then buried deep underground in places like old oil fields or gas fields. If this worked, it would be very good. It would help deal with the root cause of there being too much carbon dioxide in the atmosphere due to our emissions. The problem is that it's largely untested technology, and there's a lot of uncertainty about how effective the underground storage would be. And it's also possible that this technology may be a lot more expensive than just reducing our emissions now from the burning of fossil fuels. The second type of geoengineering is the more controversial type, known as solar radiation management. The idea here is to reduce the amount of sunlight being absorbed within the climate system. So examples include genetically modifying crops to make them more reflective, adding mirrors in space to reduce the amount of sunlight reaching the Earth, or adding sulfate aerosol to the stratosphere to mimic the cooling effects that large volcanic eruptions can have. This is what's illustrated in this particular schematic. The problem is with these solar radiation management techniques is they don't deal with the root cause of our greenhouse gas emissions. So they wouldn't avoid problems like ocean acidification and the impacts that might have on ecosystems. They also, even if they were to be effective with cooling the Earth, they may also impact rainfall in a way that's negative. So for example, we looked at one particular possible solar radiation management method using a global climate model in this paper, which was published in August this year. The idea is that it's been suggested that nutrients could be added to the ocean to promote the growth of marine phytoplankton, basically algae, and these marine phytoplankton could remove carbon dioxide from the atmosphere. So this method, which has been talked about for quite a long time, is actually a proposed carbon dioxide removal method. A possible side effect of this is that marine phytoplankton can release a sulfur-containing compound known as dimethyl sulfide, which can form sulfate aerosol in the atmosphere. This sulfate aerosol can scatter incoming solar radiation back to space, known as the direct effect, and may also impact clouds, known as the indirect effect on the climate. So, as well as being a possible carbon dioxide removal method, ocean fertilization may also act as a solar radiation management method. In our particular study, we ignored these three aspects on the bottom left and instead focused on the question of what might happen to the climate if the dimethyl sulfide emissions increased. Using a state-of-the-art global climate model, we found that the increased emissions of the sulfur-containing compound may be capable of reducing the surface temperature, beneficially offsetting global warming across most of the world. However, there was a negative impact on rainfall, with many regions receiving a lot less rainfall, which may impact livelihoods as well as ecosystems. So this is potentially a very bad side effect. It's also worth noting that we didn't investigate the impacts of the ocean fertilization on marine ecosystems. So there may be bad side effects there affecting the ecosystem, affecting global fish stocks. So I would not recommend that we rely on any solar radiation management geoengineering method as a way to combat climate change. Firstly, in practice, these methods may not work. And secondly, even if they were to work, and even if they were to reduce the warming at the surface, they may have very negative impacts on rainfall and other ecosystems. But I suggest that more modelling work needs to be done to look at these different impacts and to investigate potential dangers of these climate engineering methods. There is only one reliable way to mitigate climate change, and that is to rapidly reduce our emissions of carbon dioxide and other greenhouse gases from the burning of fossil fuels, from agriculture, and also from deforestation, especially tropical peatlands. This leads on to the final part of the talk, where we can briefly explore how can we respond to the challenge of climate change. I'd suggest that there are many different skill sets and career paths that can contribute to environmental sustainability. Musicians, artists, filmmakers can raise environmental awareness through films and through art and music. Lawyers and policymakers can work hard to develop policies, legal instruments, international agreements that actually work. I think this is really hard, so I have the utmost respect for policymakers and lawyers who can actually come up with mechanisms that do work to reduce emissions. Engineers and scientists can work hard to develop low carbon technologies that are commercially viable. The problem with many renewable forms of energy, such as solar and wind, is the problem of intermittency. The sun doesn't shine all the time, and the wind doesn't blow all the time. At the moment, the storage technology isn't up to scratch. The batteries aren't good enough or cheap enough. There are promising technologies that are emerging, such as liquid metal batteries, but a lot more work needs to be done to develop new technologies and to make them commercially viable. Physicists and chemists can seek to understand how the climate system works. Hopefully some of this information will then be useful for policymakers and for countries seeking to adapt to climate change impacts. But responding to the challenge of climate change isn't just for professionals. We can all make a contribution through our individual lifestyle choices. Let's look at some carbon footprints. I'm not an expert in this area of life cycle assessment of different products and activities. Most of the figures I use to construct these graphs are from online sources or other publications. So let's look first at the carbon footprints associated with different sorts of transport. The y-axis here represents carbon dioxide emissions in tonnes per year, so high numbers are bad. If you were to drive from Paya Lebar to NUS and back every day, you'd cover a distance of about 15,000 kilometres in 1 year. If you were to drive that in a Mercedes-Benz S-Class, this would result in about 3 tonnes of carbon dioxide being emitted. If you drove it in a smaller Toyota Prius hybrid car, that would be about half as much carbon footprint. Many of the SMRT taxis now in Singapore are actually Toyota Prius hybrids. If you were to do that commute by bus or MRT, the emissions would be far less, assuming that the bus or the MRT train isn't too empty. What about flying? I tend to visit family in the UK about once a year or so. And that's a distance of about 22,000 kilometres return, and flying economy class, which I do, would result in about 2.5 tonnes of carbon dioxide emissions. Interestingly, the emissions per kilometre for flying are actually comparable to driving a car. The thing that makes flying so polluting is that the distances are so very vast. What about diet choices? When food is grown and transported, that can result in emissions of carbon dioxide and other equivalent greenhouse gases like methane. If you have a typical medium meat diet in the UK, using UK statistics, this would result in emissions of about 2 tonnes per year. If you're a vegetarian, that's great. The emissions would be about 0.5 tonne less. If you're a high meat eater, that's not great. Your emissions are probably about 0.5 tonne more. Even more if you eat lots of beef. Because beef can be particularly bad for the environment. Compared to eating 1 calorie of milk or chicken meat or eggs, 1 calorie of beef is responsible for 5 times as much greenhouse gas emissions, 11 times as much water use, and requires 28 times as much land. So eating lots of beef is not sustainable. I'm not suggesting we shouldn't eat any beef. I don't advocate a complete boycott, but we can work to reduce our consumption of beef and be thankful for the times that we can enjoy it on occasion. I do still enjoy steak occasionally, but certainly not every day. I reckon my home electricity usage is around 1 tonne of carbon dioxide per year, primarily as a result of using air conditioning to sleep. And consumer products like a MacBook also have a carbon footprint. So a MacBook across its lifetime, including manufacturing, is responsible for around 0.5 tonne of carbon dioxide. Clothes and pretty much every other product also has a carbon footprint, so it can add up. So, to summarise, how can we respond to the challenge of climate change at a personal level? We can all think about our transport choices. We can think about our diet. Remember, less beef, that's healthier too. We can turn air conditioning and lights off when not in use. We can remember the 3 R's: reduce, reuse, recycle. Do I really need a new phone? Do I really need more clothes? And when buying paper products, we can look for products which are either recycled or carry the FSC, Forest Stewardship Council logo. I understand this to be one of the more effective certification schemes for sustainable paper products. Actually, about 2 weeks ago, Sheng and Fair Price pulled many of their non-FSC products from the shelves in response to the haze crisis. So by buying more sustainable paper products, we can help respond to the challenges of climate change and the haze, as well as seeking to protect the tropical rainforests and the biodiversity associated with them. There is no silver bullet for responding to the challenge of climate change. Carbon dioxide emissions are such an ingrained feature of our global economic system. It's going to be hard to reduce our emissions. It can take a long time to turn a ship, but it can be done. So let's start by making a difference now. Thank you for listening.